Hello everyone. Today we are going to talk about tensor products of maps. So you have been introduced to the concept of maps in the last few videos. So if you remember correctly, that if you have a ket vector, which is a two component column matrix, let's say A and B, then a map in general in this two-dimensional space will be a 2 by 2 matrix in a form like this something, and it will map you to a new vector A prime and B prime, right? So what happens if you take tensor products of these maps? All right, that can be a valid question. So let's say let's first define two maps like this, linear maps. So this is A, B, C, D, let's say, and you have another map which is P, Q, R, and S. All right. So now, if I ask you, what is this thing? All right, then you can easily see that this map is now mapping V2 cross V2 to an element in the same space. All right, if you remember that these were the tensor product spaces. For example, when you're dealing with multiple qubits, in this example it's for 2 qubit, then for 2 qubits it will be a map from V2 cross V2 to another element in V2 cross V2. All right, so now let's see how does this thing work, right? Let's say that the basis element for this space is something like this: I tensor J. All right. Okay, I have introduced some notations. So I'll sometimes write it like this without giving this cross notation. It means tensor product, and I'll just write it like this: IJ. These things all mean the same. So please be careful whenever I use it. It will mean the same thing. All right. So the basis element here means that I and J will belong to this set of 0 and 1. So it can be either 0 or 1. So when you're dealing with V2 cross V2, it can have 4 combinations, right? So it can have 0 0, 0 1, 1 0, or 1 1. These are the 4 combinations, right? So what does this operator do? This operator, A cross B, acting on IJ, acts like this: A on I and B on J. All right, this is a definition. This is how a tensor product of maps acts on vectors that belongs to this A cross B spaces. So now from this definition you can easily prove that if you have a tensor product vector, for example, if you have a vector like this in general, V cross W, then you can say that this will be mapped to, okay, I think I should not use this arrow sign here. I should rather call it equal. Okay, then this will be mapped to A times B and B times W. All right, check carefully. This first equation is defined only for the basis elements, and using this definition you can prove this for any general vector, because these are linear operators and these vectors can be written as a combination of these basis elements. So you apply it and you can prove this. All right, so now you can ask a question: how does this matrix look like? Now it's pretty simple. It will be if this is a 2 by 2 matrix and this is a 2 by 2 matrix, then your tensor product will be a 4 by 4 matrix. Let's explicitly work that out and see how does it work. So this will be A, B, C, D, tensor P, Q, R, S. All right. So now, if you want to multiply, you can write it in a block diagonal form. So it will be easy for you to understand. From the definition of tensor products, you can see that this should be A times capital B, where B is a 2 by 2 matrix, and here B times capital B, C times capital B, and D times capital B. And now you can put the value of B. Now this will be A times P, Q, R, S, B times P, Q, R, S, and this will be C times P, Q, R, S, and this should be D times Q, R, S. All right. So now if you write it down explicitly, you'll get a 4 by 4 matrix, which is AP, AQ, BP, so as promised, this is a 4 by 4 matrix. So, and these are the elements. All right. So there are some special cases where rather than considering this operator, I can consider this operator, where I means an identity operators, and I means an identity operator, and this 2 means that this is a 2 by 2 identity. So it is like this, 1 0 0 1. All right. So what does it mean? It means that if you are dealing with a V2 cross V2 space, that means from a physical perspective, this is a space of 2 qubits, then this operator will act only on the first one, and the second one will be left unchanged or unaffected because you have an identity here. All right. Similarly, we can construct this I2 cross A, and then this will act on the second qubit, and the first qubit will be left unaffected. All right. So we will work out a specific example in the next video where you will learn about these operators and how to manipulate them in Dirac bracket notation. All right. So thank you so much.